Hi everyone. Today we are going to see eigenvectors and eigenvalues. What are their importance? Okay, eigenvectors. These are essential for data analysis and dimensionality reduction in case of machine learning and data science. Eigenvectors are vectors which will not undergo direction changes during transformation. So you please note this um, sentence, that is eigenvectors. So if we have a set of vectors, or we have a vector space, and we apply some kind of linear transformation on it, okay, then even after this transformation, if some vectors remain unchanged with respect to their direction, those vectors are called eigenvectors. Suppose in this vector space you have many vectors like this, okay, and when you apply some kind of transformation, linear transformation on this, these two vectors, okay, and most probably the reverse direction also, okay, these two vectors, we can take this as two vectors. These two vectors are not changing its direction, and when you consider the other vectors, these vectors are all changing its direction. So in that case, we call these two as the eigenvectors. Okay, so when we apply a transformation on a vector space, if some vectors do not change their direction, we call them as eigenvectors. If all the vectors change their direction, then what means there is no eigenvectors existing there. Okay, that is the meaning. So if we have a set of vectors or the vector space and we apply a transformation, and if some vectors remain unchanged with respect to their direction, then we call them as the eigenvectors. Okay, so it will not undergo direction changes or span changes. That are eigenvectors. So let's see some example. Okay, so when we apply linear transformation on a vector space, the vectors that do not change their direction after transformation are called eigenvectors. And what is eigenvalue? The amount of change happened to the eigenvectors. Okay, amount of change happened to the length of the vector. That is the eigenvalue. The amount of change in length, not in direction, is called the eigenvalue. Okay, so eigenvalue is eigenvectors. They are connected. We say that the eigenvalue of an eigenvector is this much. Okay, that is the thing. Then, when we consider a square like this, so square in the sense it is a vector space. Okay, it is a set of vectors that is in the form of a square. And we can apply some linear transformations like this. Okay, this could be this is the scaling in y direction. Okay, so there will be changes to the y coordinates here. Then we can have shearing like this. That means we are pulling the vectors to one direction, to in x direction. Okay, so that is it. Then so scaling is one linear transformation, shearing is another linear transformation. And what happens to the vectors when we do these kind of scaling or transformations? Okay, so we, for example, we take this vector space contains many vectors, but we for simplicity we are taking only 3 vectors out of these all vectors. Okay, so one vector is on the x direction, that is the green colored vector. Then one is on the y direction, purple colored vector, and one arbitrary vector in 45 angle with the x-axis. Okay, that is the z vector or orange vector, we call it them as. Okay, then let's see what happens if we scale this vector space in y direction. Okay, So when we scale it, what are the changes happen to these vectors? So let's see. So this is what happens. That means the direction, when we consider these three vectors, the direction of x and y vectors, that means this green and this purple vectors, they do not change their direction. They are pointing in the same direction even after this scaling. Okay, but when we consider this orange vector, that changes its direction, because initially it was 45-degree angle with the x-axis, but now it is changed. So that means the direction of that vector is getting changed during the scaling operation or during this transformation. So what we can conclude is that here we have two eigenvectors. One is in the x direction and the other one is in the y direction. Okay, so these vectors do not change their direction during the transformation, so they are the eigenvectors. And what is the eigenvalue means the amount of change happened to the length of these eigenvectors. Okay, so let's see it one by one. So considering the two transformations, scaling and shearing. In the scaling that we have seen here, in scaling in y direction, x has the vector x has no change in span or in direction, so we call it as an eigenvector. So no change in length. So what does it mean? Its eigenvalue is 1. That means the change in length after transformation, that is eigenvalue, okay, corresponding to an eigenvector. Okay, we always say eigenvalue corresponding to an eigenvector only, not to any other vectors. Then what about y? Y has no change in the span, so that is also an eigenvector. Then length of the vector is doubled, so its eigenvalue is 2. So change in length is twice the length of the previous one, so the eigenvalue is taken as 2. Okay, it is doubling the length. And what about the z vector? Z vector, that the orange one is taken as the z vector. It has changed its span as well as its length. So since it changes its direction or the span, we cannot take it as an eigenvector. It is not an eigenvector, and so it has no, we are not considering its value also, change in length. So it is not an eigenvector, and it does not have the eigenvalue. Then the other example is shearing. So let's see shearing, how it happens. See, initially it was like this. Okay, everything we take the same set of vectors, and three samples we have taken in x direction, y direction, and in 45 angle with the x-axis. Okay, and after shearing, what happens? The direction of x remains same, so there is no change in the x vector, but for the other two vectors they have changed the direction. Okay, so we can say that this is the only vector that is not changing the direction, so it is the only eigenvector in this transformation in shearing. Okay, so y and z change their span, and x does not change the span and length. And since it is not changing the direction, it is taken as the eigenvector, and there is no change in the length as well. So the eigenvalue is 1. Okay, then next is the rotation. Let's see what happens in the case of rotation. Okay, so what happens in rotation? All the vectors change their direction. Okay, all vectors change their direction. So there is no vector which remains in the same direction after the rotation. So there is no eigenvector in this case. Okay, so x, y and z change their span, so no eigenvectors exist in this transformation. Okay, so hope you understood that much. Then the eigenvalue equation. Then how we algebraically calculate the eigenvalue and how to find out the eigenvectors. So for that we use this equation Ax is equal to lambda x, where A is the matrix that represents the transformation. Okay, A is the transformation matrix and x is the eigenvector and the lambda is its corresponding eigenvalue. Okay. So A is representing the transformations like the shearing or scaling or rotation, all those things. Okay. And this is the equation we use. This is the eigenvalue vectors. That means the transformation eigenvector. That means it remains the same even after the transformation. So the change is with the lambda only. Then we can rewrite the equation like this: Ax minus lambda x equal to 0. So that will be rewritten like this: A minus lambda I is the identity matrix, lambda I into x is equal to 0. So when this condition is satisfied, the determinant of A minus lambda I should be 0. Okay, so based on this third equation, we are going to find out, based on this equation, we are going to find out the lambda values. Okay. And after finding out the lambda value, we have to find out its corresponding the eigenvectors x. Okay. So for example, we take an eigenvalue for this transformation matrix A, 4, 2, 1, 3. Then its characteristic polynomial is written like this: P of A lambda is equal to determinant of A minus lambda I. We take it as 0. Okay. Then what is A? A is the 2 by 2 matrix that is given here. And lambda we have to find out. I is the identity matrix. So we write it like this: 4, 2, 1, 3 minus lambda 0, 0 lambda. And take the determinant of that subtracted result. It will be like this. Then finally it is like this and it is equal to 0. So what happens? We can reduce it like this: 2 minus lambda into 5 minus lambda. So finally lambda values could be 2 and 5. So in order to distinguish these lambdas, we put it as lambda 1 and lambda 2. So lambda 1 lambda value is, eigenvalue is 2. The other eigenvalue is 5. Okay. Then we found out the eigenvalues like this: eigenvalues lambda 1 is equal to 2 and lambda 2 is equal to 5. These are the two eigenvalues. Okay, then what is the sum of these eigenvalues, lambda 1 and lambda 2? That is 5. 2 plus 5, it is 7. And there is a relationship with this value to the matrix A. So when you find out the sum of the diagonal elements of this vector, we will get the same answer, 7. 4 plus 3, that is also 7. Okay, so that means the trace of matrix A is equal to the sum of its eigenvalues. Okay, so this relation exists there. Okay, so keep it in mind for future reference. Then we have to find out the eigenvectors corresponding to each eigenvalue. Okay, so x is the eigenvector. So we use this equation to find out the vector for a minus lambda I into x. Okay, so this is the equation. We have to submit the substitute the lambda values here. So when lambda equal to 2, it will be reduced like this: 4 minus 2 is 2 and 2 minus 0 is 2. Then 1 minus 0, 1. 3 minus 2 is 1. Okay, so that is like this. So it means that when you multiply this, we get a 2x1 plus 2x2 is equal to 0 and x1 plus x2 is equal to 0. That means that this x1 equal to minus x2 or x2 is equal to minus x1, whatever. Okay, so the vector x1, x2. Okay, so here the vector x is written like x1, x2 because it is a 2 by 2. A is a 2 by 2 matrix, so it is a two-dimensional space. Okay. So in a two-dimensional space, every vector will have two coordinate values. So that's why we have written x1, x2. And if it is a 3 by 3 matrix, or it is a 3D space, what we will write? It will have three components: x1, x2, x3. So that is why it is like this. Okay, so that is why the eigenvector has two components over here. Okay, so x1, x2, the vector, first eigenvector can be written as 1, minus 1. Okay, or minus 1, 1, whatever. Then for lambda is equal to 5, when you substitute 5 here instead of lambda, we will get the matrix like minus 1, 2, 1, minus 2 into x. Then when we multiply it, we get minus x1 plus 2x2 is equal to 0. That means that x1 is equal to 2x2. Okay. So how the vector will be? It will be what it is? It will be like 2, 1. Okay. So x1, x2 is equal to 2, 1. Okay, x2 is the half of x1. So in that terms, we have written 2, 1. So these are the eigenvectors corresponding to these eigenvalues. Okay. So for the first eigenvalue lambda 1 is equal to 2, the eigenvector is 1 minus 1, and its eigenspace is the span of this eigenvector 1 minus 1. Then for the second eigenvalue 5, we have the eigenvector 2, 1, and its eigenspace is the span of 2, 1. Okay. Then we have to know two terms like geometric multiplicity and algebraic multiplicity. Okay, so when we find out the lambda values, okay, and if you find out lambda is 1 equal to 3 and lambda 2 is equal to 3, that means that there are two identical values for the eigenvalues. Okay, two identical values. So we call the multiplicity as 2. Multiplicity of this eigenvalue is 2 because two identical values are there for the lambda values. So that is algebraic multiplicity. Okay, and what is geometric multiplicity? Means for one lambda value, if there are more than one, or if, how many vectors are there corresponding to a particular eigenvalue, that is called the geometric multiplicity. Okay, that means if for one particular lambda value, suppose the lambda 1 is equal to 2, and corresponding to this I get two eigenvectors. Okay, I get two eigenvectors corresponding to this eigenvalue. That means that its geometric multiplicity is 2. So we have two terms, geometric multiplicity and algebraic multiplicity. So the number of linearly independent eigenvectors associated with a particular eigenvalue, that is called the geometric multiplicity. So in the previous example, the geometric multiplicity is 1. So that means corresponding to each eigenvalue, we got only one eigenvector each. Okay. And its definition goes like this. Let lambda I be an eigenvalue of a square matrix A. Then the geometric multiplicity of lambda I is the number of linearly independent eigenvectors associated with the lambda I. In other words, it is the dimensionality of the eigenspace spanned by the eigenvectors associated with the lambda I. Okay, so when you take a lambda value, how many eigenvectors are associated with that value? That is the geometric multiplicity. And how many identical vectors are identical eigenvalues are there? That is the algebraic multiplicity. And the graphical intuition for this eigenvectors. Okay, suppose we have the scaling in the y direction as we see in the previous example. Okay, in that case we are squishing the diagram into x direction. Okay, we compress it um, into half of its length in the x direction and enlarges it into twice its size in the y direction. Okay, so when you change this vector space like this, what happens? When you apply these changes, that means stretching in the y direction and compressing in the x direction. Okay, so the length in the all vectors except these two vectors will not change. Okay, all except in the x direction and y direction, all other vectors will change their direction. Okay, so the eigenvectors are these two. And what is the lambda value? For the first one, in the y direction, the lambda value will be 2 because its length is doubled. And in the x direction, what happens? Its length is reduced to half its size. Okay, so that is lambda value is 0.5. And the determinant of A represents the area of the entire thing, area of the vector space. Okay, so that does not change here. Even after the transformation, the area remains the same. Okay, so in order to find out this determinant of A, we can apply one more thing, lambda 1 into lambda 2. So when we do the multiplication of this lambda values, then also we get the determinant of A, or the area of the vector space after the transformation. Okay, then this is shearing. In the case of shearing, only in the x direction we have the eigenvectors. All other vectors will change its direction. Okay, so this direction and its opposite direction is also taken. So its eigenvalues are 1 because there is no change in the direction. No change in the length. So it is 1. And determinant of A will be lambda 1 into lambda 2. It remains same. Okay, so determinant of A is 1 means there is no change in the area. It remains the same. Okay, then rotation. We have seen in the previous example, like in rotation, all the vectors change their direction. So that means there is no eigenvector. So when we try to calculate the eigenvalue, we will not get any real number as the eigenvalue. So here we have got the complex numbers as the real as the eigenvalues. So there is no real value for this eigenvalues. So that means that there does not exist any eigenvector. Okay, and determinant of A remains 1 because there is no change in the area. And we are squishing this two-dimensional vector into a one-dimensional space, elongated one-dimensional space. So what happens is the vectors in this line will be remain in the same direction, and all other vectors will change their direction into this, or we are actually projecting it into this direction onto this line. Okay, so all the vectors, what happens? This vector will reduce its size to 0. This vector will also reduce its size to 0. Okay, so all these vectors will change their length to 0. So that means lambda value is 0 because its length is reduced to 0, and only the vectors in this direction, they elongate their length to twice its length. Okay, so that's lambda 2 is equal to 2. And what is the area? Lambda 1 in lambda 2 will give you 0. That means that in one dimensional we have no concept called area. Okay, area is 0 in one dimensional or for the line. Okay, so that is the thing. Then shearing and stretching. What happens? These two vectors we can see in 45 angle with here and here. Okay, these two vectors, they do not change the size direction. All other vectors will change the direction, and the change in length is not like this. This vector will reduce to half its size, and this will be 1.5 size, increases by 1.5. Okay, So there is a change in the area also. It is reduced to 0.75. Okay, 3/4 of the original area size. Area. Okay. Then the remarks, the eigenvectors x1 to xn of a matrix A belongs to Rn by n with the n distinct eigenvalues lambda 1 etc. lambda n are linearly independent. Okay, so eigenvectors are linearly independent. A square matrix A belongs to Rn by n is defective if it possesses fewer than n linearly independent eigenvectors. Okay, then the determinant of a matrix A is the product of the eigenvalues that we have seen in the example. Like we have the lambda values, and when we multiply lambda 1 into lambda 2, we will get the determinant of A. Okay, so this is actually the product of lambda values, and the trace of a matrix A is the sum of its eigenvalues. That also we have seen. Then the spectral theorem, if A belongs to Rn by n is a symmetric matrix, then there exists an orthogonal basis of the corresponding vector space V consisting of eigenvectors of A, and each eigenvalue is real. Okay, so we can find the base vectors as the eigenvectors of the matrix A. Okay, that's all about the eigenvalues and eigenvectors. Hope you understood this much, and thank you for watching.